Well, I'll fix it. Are you ready, Shaukat?
Yes.
Okay, welcome everyone. So today we have Shaukat Ali. He's going to talk about black box testing of quantum programs. Shaukat is the head of the Department of Engineering of Complex Software Systems at Simula Research Labs. I think he will talk a bit more about Simula and the department and himself. So I will just give the floor to Shaukat.
Thank you very much, Luis. So I will just start. So yes, so the outline of my talk would be that I will quickly talk about my department at Simula and what kind of research we are trying to do at our department in related to quantum software. And then I will try to convince you that why quantum software testing is important, and then followed by one of our recent work, which was done by our master students. I'm going to present that work. So let's start with my department's overview. So in complex SC department, which is engineering complex software systems, so we focus on the research in developing complex software systems such as cyber physical systems, Internet of Things in various domains such as oil and gas, maritime, and so on. And we try to focus on all the phases of development of software systems such as requirements engineering, design, development, and testing. But the ultimate aim is to make software system much more secure, dependable, and so on. And in our research, we try to apply different kind of methods. We do a lot of modeling, model-driven engineering, and so on. And recently, we are also looking into digital twins and various simulations during the design, development, and testing of cyber physical systems. And we also apply a lot of such algorithms, such as genetic algorithms, for such as optimization and so on. And we also have started to apply various machine learning techniques in our works to support the development of complex software systems, such as reinforcement learning, rule mining, and so on. And a couple of years ago, we have also started to look into this new area of quantum software engineering, which will be the focus of my talk today. So a quick overview, we are two key scientists in our department, my colleague Tao Yue and myself. And currently we have roughly these members who will be working on various projects, not only on quantum software engineering, but also my colleague Tao is affiliated with the Nanjing University of Aeronautics and Astronautics, and she has quite a big team there with more than 18 masters and PhD students as well. So together we have quite a few number of people who will be working on a lot of different topics in our departments together. And we have quite a bit of collaboration in China, in Japan, in Europe, the University of Porto, including Mondragon University, Malaga, and so on. So this is roughly the overview of the department is. And now, and as I mentioned, then recently we have started to look into quantum software research. So what we are focusing on is roughly summarized here. So we are the two scientists who are leading this quantum software engineering area in the department and also at Simula level. And we're focusing on developing different methods such as quantum software modeling, coding, testing, and debugging methods. And we are also looking for quantum and search and optimization, especially for optimizing the different phases or different activities in such development of cyber physical system and so on. And our research director, R. Magnus, he's also focusing on, because he comes from this background in high performance computing and scientific computing. So he's taking a lead from high performance computing side. For example, how can we host different quantum computer emulators on this national experimental exascale computing infrastructure that Simula hosts. So idea is to deploy and provide this access to different research organizations, companies in Norway, so that they can do experiments with quantum computers. So our focus is on doing groundbreaking research on quantum software development. And our aim is to make real world practical and dependable quantum computing applications cost effectively. And we want to work on the applications which are beneficial to society and industry. So this is roughly the focus of this quantum software engineering research in our department. So now coming towards one idea that why we need quantum software testing, because when I talk to a lot of people, especially from different domains, they always have these doubts that why we need, we can just run program with all the inputs, we can try it out, and it's enough. Why we need something special for quantum software in testing? So I just give some example that software is all around us. If you look at, for example, aeroplanes like 787, Dreamliner has approximately 6.7 million lines of code. Look at the card, for example, Volt has about 10 million lines of code. Android operating system has up to 15 million line of code. Google, if you combine all its services together, it has 2 billion line of code. And what we are trying to do, I mean, all of us, I mean, who are interested in quantum computing, we are going to make all these applications, we're going to deploy all this quantum software on all these critical applications. So it means that all this complex system in medical simulations will be using quantum software. But we see that the software will be everywhere. So does the software failures. And you can find examples very easily if you look around newspapers and so on. For example, in 2014, 11 million people were affected due to a software bug in 9/11 emergency services. 2014, there were 20 inmates which were released from the prison because of a software bug. There was a problem with the Obamacare system when they launched, and it went right away down, this online insurance system, due to a software bug, and so on. If you look around, you will keep finding all these software bugs. So it means that no matter how much we do, there will be software failures, and you have to make sure that the software is safe and reliable. And for example, if you're following this Mars helicopter in Unity, it has some problem with the code, and it was telling that okay, there's something wrong, and it couldn't take its flight, but it was actually, there was no fault. So you never know that how this software which we are going to deploy on different critical system, how it's going to behave. So we need to ensure that the software systems are safe, reliable, and dependable. Thus, we feel that we need new quantum software testing methods for developing complex software systems that are dependable, safe, reliable, and so on. I mean, if we look back into 1960s or even before, when the classical software was being developed, we see that people didn't realize much importance of software testing until things started to go seriously wrong. For example, we know about Ariane 5 crash and Thelak 25, which was another medical device which has software fault, which was giving then high doses of radioactive therapy to the patients and so on. So it means that we need to realize that we should start thinking about quantum software testing right from the beginning when we are building the foundations of quantum computing applications. We should not just wait until something terribly goes wrong and then we try to start building some methods for automated software testing, method for quantum computing applications. So this is our view is, and I think it's going to be very important in the future that we have these methods ready to test the applications that we're going to build. So that was roughly some of the background that we had and why we need quantum software testing. So then we started to investigate some methods on how to test quantum software or quantum program. And we did this work, actually one of our master students, she did this work where she tried to define different coverage criteria on the inputs and outputs of quantum programs. And the idea is that how we can see that quantum program, if given an input, produce the correct output or not. So if you think about this idea, this is similar to what we have been doing in the classical computing. So there's not something very special here for the quantum computing that we did, and that's why I named our I named my talk about as black box testing of quantum programs, because we will just focus on the inputs. We treat quantum program as a black box, and we just observe the outputs after reading the measurements. So it means that we are not touching the quantum program during its in superposition and so on. And of course, doing that has its own limitation that I will discuss later. So what I mean by inputs and outputs of a quantum program. So we defined that input is the values of qubits after we initialize a quantum program. And again, I could say that this definition is very limited. So depending on how we evolve things in quantum programming, we may need to redefine what do we mean by a quantum program's input. But what we assume that if you look at a simple entanglement program here, which has 2 qubits, qubit 1 and qubit 2, and Here we could see that it has two inputs. So it means it has in total 4 values. And we call these as inputs. These are my inputs right after the initialization. And at this moment, if you see that we have 2 small zeros, which says that this quantum program is initialized to 00 qubit. And then if we look at what we define as an output is that something that we observe after measurement. So it means that if you look at the end of the quantum program or quantum circuit, here you can see that the values are 00. So, so this is what we define as a output. So what we are trying to focus, the main idea behind is that how can we define different coverage on the inputs and the outputs of a quantum program and see that how these input and output coverage criteria are effective in finding different kinds of faults in quantum programs. That's the simple idea we tried. And it is quite similar to classical testing classical programs. So we could say that we just tried a classical method of testing on a quantum program. So when we are going to test our quantum program, we need some sort of program specification. It means I need to know what is the correct output. Otherwise, I cannot say anything. So first, we need to have some sort of inputs. The input should be valid. It means that it might be, it is not always true, but it may be that there are certain subset of values of inputs that are valid for a particular program. So we call them as valid inputs. And then a program can have a certain output values out of all possible values, which we can say they are correct according to the program specification. So it means that we need some sort of this program specification to test the quantum program. And as we know that we have quantum programs are probabilistic, it means that it may be the case that if I run program with one input, I observe an output with a certain probability. Maybe 50% of the time it's 0, 50% of the time the output is 1, and so on. So it means that there will be probabilities associated with each output as well. Let's look at this example. So it's again a very simple quantum entanglement program. And we can see that in the table on the first column that let's assume its valid values are 0 and 1. So it means that this program will give me only correct output if I initialize it at to 0 or 1. This is my simple example. But since we have 2 qubits, so the possible options are 4. So I could initialize this program as 0, 1, 2, and 3. But let's say the valid values in this case out of 4 are 2, 0, and 1. And for each valid input, you could see that we have corresponding valid output and their probability of occurrence. So if I give input 0 to this program, according to my program specification, I should observe 0 50% of the time, and I should observe 3 as 50% of the time. Similarly, if I do the valid input as 1, I will observe 0 and 3 with 50% probability. So we have valid output values, which is 0 and 3. And corresponding to each, we may have the probabilities which are according to program specification. And we have to admit that it is not that we always have this program specification available. So it may be that we have a partial specification available, or in certain cases, we may not even have specification. So then we need to try out different methods, such as metamorphic testing and so on. Just an example, let's say I initialize my quantum program to 0. So you can see that I'm showing the program state on the right side. So you can see that 0, 1, 2, 3 are the 4 possible state because we have 2 qubit program. And with this statement, my program is initialized to 0. It is the same as classical program because it's 0 and there is no probabilities. And then in line 8, I apply Hadamard. So now my program goes into superposition. And now it means that it's 0 and 1, and these filled circles shows the magnitude of each value. It means that if I read now my program, there's an equal probability that 50% probability that it will be either 0 or 1. And then now I entangle these bits together, and my program state in superposition will look like this, 0 and 3. So now if I read my quantum program, which is a measurement I'm calling, I will either get 0 or 3. And probability of occurrence of 0 and 3 are 50% each. So it's something like this. So it will be either 0 or 3. This is how this program is working. So but there are a lot of challenges in testing quantum program. I mentioned a few. First of all is probabilistic nature. We see that the output is probabilistic. It means that corresponding to each input, I will observe output with a certain probability. So we need to take into consideration this probabilistic nature. Then when we have to touch the program during in superposition, there is no direct way to do that. When you try to do that, you will lose superposition and then program is gone. So you cannot measure it the way we do it in typical program that we assert something after each step and we cannot do that. If we do that, then this superposition will be lost. And then lack of precise test oracle. This is a big problem. We for a big program, let's say with 20 qubit, 30 qubit, we will not be able to get exact probabilities associated with each input. So it means that we need to work with very maybe imprecise test oracle or maybe no oracle at all. And there are many other challenges. For example, our hardware is so noisy. We need to do with hardware errors. We need to deal with decoherence, and all those things have to be taken into consideration to build these testing foundations for quantum programs. So in our this framework, in simple framework, we did three things. First, we defined three coverage criteria on input and output of our quantum program. So we call them input coverage, and input-output coverage. And then since we need to check whether the output is correct, we define two types of oracle. One is wrong output oracle, output probability oracle. And then to assess, we did mutation analysis. And I will explain these three steps now. So now, first of all, the coverage. So if you look at input coverage, it's a very simple concept. So we want to generate a test suite such that there exists a test for each valid input. So we can statically define this test suite very easily. So for example, if you look at my same program and we saw that the valid input were 0 and 1. So one possible test suite is 0 and 1. That's it. And we can observe output 0 and 0 if we run the program, for example. So this is my simple input coverage. So it means that we generate one test case per valid input. So if I have 20 valid input, there will be 20 test cases. If we have 40, we will have 40 test cases in the test suite. Now output coverage. It's in output coverage, our aim is that we want to observe each valid output exactly once, at least once in the test suite. And since we are talking about observing output, it means that we cannot generate this test suite statically. We have to execute, observe the output to see that if we covered all the outputs or not. So if you look at the same program with the same specification, we could see that one possible test suite may look like this. So I gave input 0, I observed output 0. I gave input 1, I observed output 0. I'm still missing the other valid output, which is 3. So I gave again 0 and I found 3. So this could be one possible test suite. And you could see that to generate test suite, which covers output coverage, I have to run the program. So it means that cannot be achieved statically. Then input output coverage, the concept is same. So what we want to do now is that for each input, I want to observe corresponding valid output at least once. And again, to achieve this kind of coverage, I need to execute my program. I cannot generate this test suite statically. Now look at the example. So see, in this case, for example, I gave input 0, I observe 0. I gave input 0, I observe again 0. I give input 0, and then I observe 3. So now you can see that corresponding to the valid, the corresponding outputs were. Now I do the same for input 1 and 1. And then I can see I observe because the output is not correct. So let's say this is again the same example I had, and let's say I run like this. So I gave input 0 and I observed output 1. But if I look at the program specification in the table on the left bottom, 1 is not the valid output for this program. So it means that this is the wrong output is observed, and then we mean that the program is definitely failed. Then there is one second test oracle we call it as output probability oracle or OPO. And this one is that the program produces the correct output according to the specification, but then there is a variation in in the in the expected probabilities that we need to check. So, so it means that we can have two cases. For example, the program could fail with a certain confidence. We can say that, okay, let's say the output 3 has to be 50%, and then we observed 48%, and we do some statistical tests, and we can find that the program is likely failed. And then, of course, there could be another case that we do the statistical test, but we don't find significant difference. But we may say that program pass or fail, but it's inconclusive. We cannot say something definitely. So this is how it works. So we have a valid input, we give it to program. And according to program specification, let's say we want to observe output O with the given probability. This is the correct, this is my oracle. And then when I execute the program, I observe an output with a certain probability. And then I can compare these two probabilities with some statistics to see that if it is correct, the observed probabilities are correct according to the program specifications or not. So this is the same example I have been using. And then in this case, let's say that there are 10 different groups, and we can see that 100% of the time we observed only one. The probability of observing one of output 3 was always 100%. So but according to my program specification, if you look at on the top, I should observe 0 50% of the time, and I should observe 3 50% of the time. So if taking this graph as input, I do a statistical test, I would find that the p-value would be less than, it would be very small. And this tells me that the program is failed. And now look at another example where we have different values. We have sometimes we observed, for example, if you look at group 1, we observed output value 349% of the time, we observe 51% of the time 0, and so on. So there are different groups. And if I try to do statistical tests, the probability value will be greater than 0.01. So it may tells me that the program is not failing, but it's kind of not passing as well. We cannot say anything definitely, so we kept it more inconclusive at this moment. But of course, we need to further look into more fine-grained definition of these oracle values that likely fail, pass. What does pass mean? What does inclusive mean? But in this paper, we just things a little bit more open. So now, as the third thing was that how now we have defined input and output coverage criteria, and we also have these oracles by which we can check if the program is passing or failing. We can do that now. But how do we assess different coverage criteria now? And when we started to do this work, it was difficult to find some open repository with a lot of faults and bugs and so on. So there nothing like that exists that we can find easily for classical programs. So there was no way to find those things. So I think that in some point in the future we need those kind of repositories so that we can assess our testing techniques for quantum programs. So we did a very simple and very brute force thing. It means that we did different kind of additions on the correct program. For example, add gate. So we introduce a gate on one of the qubits of the program. Let's say this is my correct program. To introduce the fault, I can add, for example, another Hadamard gate on the qubit 1. So this is my mutant with add gate, and then I run my input coverage test cases, output coverage test cases, and if I see that if they find this bug or not, or fault that I seeded. Similarly, we deleted some gated. We also replaced one gate with another equivalent gate, and so on. In this way, we define these different mutation operators. And I would like to mention that there were some previous work we did the same. They also have the similar kind of these mutation operators to seed faults in quantum programs and assess their effectiveness. So we use the similar approach as them to assess our input-output coverage criteria. Then we selected a few programs from one of this book that we were experimenting with. We generated in total 2,000 test suits, and each group had 100 test suite as a group. So, and we use this one sample Wilcoxon test with 99% confidence interval to assess if we pass or fail. or we go to likely fail or inconclusive test result. And of course, there were some parameters in our approach which we had to set somehow. And of course, there is no, at this moment, we don't have any guidance or something based on which we can choose these parameters. So we just choose them. And we will try to do more experiments maybe in the future to see whether to use 20 test suits or 50 test suits and so on. Then we use the typical criteria of mutation score. It's the same formula that we use in our research, that we just say that, okay, if I run one test suit, I can see that how many mutant programs are killed. So let's say if total mutants are 100 and my test suit killed 20, so my mutation score is 20%. And of course, we have to take out the equivalent mutants that in the same formula so that we can remove them from the total number. And then for each type of test oracle, we calculated mutation score. And then we also have the total mutation score, which was simply the addition of mutation score corresponding to each test oracle. So mutation scores tells us the effectiveness of coverage criteria, that how good they are in finding the faults. But in terms of cost, we used this very simple criteria of average number of test suits killing the mutants. And similarly, we used another criteria, which was the total average size of test suits. It means that for each oracle. So the cost is two ways. One is we do not differentiate between different test oracles, the two test oracles. Second is we differentiate between test oracles. And then we try to study the results based on these two, mutation score and the cost by years. Some of the key results then. So when we do not distinguish between test oracle, we observe something like this. So for one of the program ENT, we achieved 80% mutation scores with various costs. So the number, for example, 2001, 2397, these are the average number of test cases. And we could see that input coverage is simpler criteria with less cost, but input-output coverage criteria is quite expensive even for a simple program. And then for the other programs, we achieved different mutation scores and different cost associated with them for input coverage, output coverage, and input-output coverage, as shown in the table. These are efficient, but looking at this result, we could easily see that even with even with this less coverage criteria such as input coverage, we were able to achieve quite high mutation scores. So it could tell us that maybe we don't need very expensive coverage criteria for simpler programs. If you have a 8-qubit program, 10-qubit program, doing input coverage might be just sufficient. And of course, if you do more expensive criteria, there is a chance that we can increase mutation scores a bit more. Now, we also studied that if we look at the difference between the two kind of test oracles, which means wrong output, and also this Opio, which is output probability oracle. So for one program, for example, we'd see that with WU, which is wrong output, we always see that if the program were to produce a wrong output, you could find it very easily with one or two test cases. That's it. But of course, if we cannot find the wrong output, we also always have to run more and execute a certain number of times. So the cost for Opio was always higher in that sense. And we observe very similar with most of our programs in a similar way. That whenever the program was failing because of wrong output, it was quick. But whenever we were trying to fail the program with Opio, it was always took much more number of test cases and the cost was quite high. So yeah, so this is what I was saying, that if the program produces wrong output, we can find it potentially with a very low number of test cases. However, if the fault is producing the correct output, then the cost of finding fault with Opio will always be higher, because we need to run each test case multiple number of times, and we need to do statistical tests to calculate those p-values. And okay, so this was the work we did, but it comes with a lot of limitations in my opinion. First of all, there is a scalability issues. I think the most of the program we tested, they were 3 to 5 qubits, something around that. So it means that if your quantum program is small, you can simply just use input coverage and be confident about your program. But when your program is going to be complex, maybe 20 qubits, 30 qubits, maybe input output will not be sufficient. It means that you need some sort of test optimization or a better way of doing the testing. And we recently, the same our master student, she did some experiment with genetic algorithm where she's trying to apply a genetic algorithm to reduce the number of inputs to fail the program. And we submitted this program paper to a conference, so it's under review. Also at this moment, as you see that the program was treated as total black box input and output. So we didn't take care of anything about the phases in the program. We didn't take care of anything that could happen in the program. So it means that in the future, we could improve these things with coverage criteria based on the structure of the program. For example, how different gates are placed at different locations and how they affect the programs. So I think these things have to be linked with this white box coverage criteria in the future. And mutation analysis, we did a brute force. So we just did all possible mutants that were possible on these simple programs. Since this program was simple, we were able to generate a lot of mutants. But if the program is big with a lot of gates, this will not scale. So it means that we also need to think about more intelligent method to generate more difficult mutants that could serve as a kind of benchmark to assess the effectiveness of different quantum programs. So I think that's all I have. So it was just one of the preliminary work we did. So then I am now open to any questions or anything.
Okay, Shaukat, thank you. This is Pedro. I'm now stepping in here for Rui, who is experiencing some technical difficulties. So I don't know if there are any questions from the audience or even from the outside. I know Ines Dutra had to leave.
Actually, let me find the chat. Okay.
Yes. Okay. There are no questions from YouTube, but there's a question here about: do you have any tests for quantum annealing type of computers?
No. So right now, I think what we are focusing right now is the quantum circuits. So we are only testing the quantum circuits, and we execute those quantum circuits on simulators. So mostly we are working with Qiskit and the quantum computer that comes with it. So not for that.
Yeah, there was also, this is a question from Andrei Lopes, and that was also a question I had in mind, is that are you targeting a specific technology, so to speak, or this is totally agnostic because it's a circuit level? Do you foresee going to a specific vendor, let's say? I know this is possible to a specific question.
So at this moment, I think we are independent of any specific vendor. So we're trying, I mean, because the project that we have in our lab is about is a basic research project. So it's
right.
So it means that we are focusing a lot on theoretical aspects. So we will try to come up with ideas which are quite low level and they are quite independent of maybe vendors. That's our aim is.
So kind of along these lines, I'm wondering if this specific domain of software testing, is it more amenable to, say, annealing kind of computers or circuit kind of computers? I'm familiar with the D-Wave and its technology. I'm not so familiar with, say, ion trapping and other technologies out there. So I'm wondering if there's one of them that is more amenable for your mapping, so to speak.
So I think for us it would be quantum circuit based at this moment.
Yeah. Okay. All right.
Yes.
So there are no questions from YouTube.
Yes.
Yeah.
So I see a question from Joao Pascual.
Yeah. I don't see it unless it's going. Okay,
yes.
Go for it.
So I can maybe first also read the question. So
yeah, please, because I don't see all the questions here.
Yes. So the question is that, do you have any guideline to predict / determine the number of executions needed for Opio? Actually, no. So was the big issue for us, that how to come up with this number. But the main idea that we're exploring is that if we didn't, I think, do it now, but we're thinking that since when we calculate the p-value, you can also sometimes can calculate this effect size. So it may be that we try to encode somehow this effect size, which can tell us that how significant this result is. Because more execution we have, we will have more confidence on the results, but still we have no guideline to select that number. So one idea could be to determine based on the effect size of the statistical test that we employed, maybe. But right now we couldn't find much, I think, as far as I remember.
So I had another question, and this goes back to this notion of when you do, my background, by the way, is compilers. So we look at static analysis and symbolic execution and whatnot. And so you mentioned that, well, there's some inputs that might not be valid because now you might not have control about all the inputs and all the paths. So in some programs, there are the so-called false paths that are never taken. I mean, do you ever get any false positives with this approach? I mean, how can you eradicate them?
Yeah, I think this might be possible, but we didn't look into this. We did very, very preliminary experiments with very simple programs, but that will happen for sure.
Right, because in the false path is basically, the logic basically means that if you take an if statement in one place, you're not going to take an if statement in the other one, right?
Yes, so we didn't reach there yet. I think there was only one program we tested which had some sort of conditional execution, but it was also very simple. So but this will happen in complex.
Right. So I'm wondering how you can then recast your problem so as to explicitly eliminate that from your input, so that you never get a probability distribution for some of those paths that are unrealizable.
Okay. Yeah, I think, yeah, I'm quite unsure at this moment, but it's a very good.
Yeah.
It could be a very good problem to solve and write a very nice paper.
Right, because it might not be simple, or it might not be very feasible to actually recast your problem so that you could eliminate the false paths, but then you eliminate also some other possible paths, and then all of a sudden you throw away the baby with the bathwater, right?
Yeah.
So there's another question here. What's the maximum number of qubits you can perform the program testing you described in this talk?
I think the maximum we had, I think, was 5 or 6 qubit. I need to check, but I think we could do similar up to 10 qubits as well. It will not be an issue, I think. But I think if it get more, then the input output become too problematic because it's too many input and output combinations. But what we did here, I think it was 5 or 6 maximum. I need to check. It's not fresh in my memory, but it was small programs. Okay. Very small circuits, I think. Yeah. Okay, there is another question from Daniel.
Yeah, I cannot see that, but I'm glad you do. Go ahead.
So I would like to know if there is significant difference running test suite with simulators or the quantum computer, and if there is, in which cases. I think, personally, I think if we run the same test suites we have on a quantum computer, the results will be very different. Because I think we didn't consider any of the noise in the hardware at this moment.
Right.
And I think we need to consider that in more new techniques, that they should be more aware of the hardware errors and decoherence and so on. And I think I asked actually my student wants to try to run these on quantum computer with Qiskit and see what kind of results we get.
Right.
We haven't done that.
Compare the languages, so to speak.
But it will be different. I'm quite sure. But in a way, I think we could, if we develop a testing technique with a quantum computer simulator with pure qubits, at least we could say that our testing techniques are correct, right?
Mm-hmm.
So it give us some confidence, of course. And then the next step, we do that on a quantum computer. So then we know that the problems that will occur, it will be either because of a problem with a quantum program, or it could also be because of the error, hardware error. So, but testing technique is correct, for example, I think.
Right. The other concern is how much of the noise will affect then your readings and so your coverage analysis, so to speak. But I don't know, I might be mixing up here the technology with the implementation itself, and so that's usually a thing.
Yeah. And I think even in this Qiskit that we are using in our other works, it's you can also simulate the hardware errors in the simulator. I think they picked that from the actual execution, and then I think we could also do some experiments, even with the simulator, but with the realistic simulated hardware errors. So that could be one thing to try out in the future works, I think.
Okay. I do not see any other question here. I don't know if you can see. I don't know exactly why. So maybe people are sending this directly to me. Can you see any other?
I see a message from Rui, so he cannot unmute himself. So.
Right. No, yeah, I also got that. Yeah, now every now and then we have these technical issues. So it seems to me a little bit of a more generic comment here. I mean, you're a small team there, right, at Simula.
Yes.
And I suspect that you have just started, just maybe a couple of years ago. So I would be curious to see maybe later on in the year or next year to have quote unquote an update on these specific topics. I'm wondering how far are people in quantum testing for programs, because this was one of the big promises of quantum computing at the beginning. And for some reason either did not materialize or is not materializing as quickly as people would have liked to. I mean, what's your take on that?
Yeah,
what's going on right at this point?
At least for me, what is going on is that I hired people and they cannot join because of Corona. So, so my project is delayed. I was supposed to do these things 2 years ago, starting 2 years ago.
Right.
And I haven't managed to get it started. And my first PhD student now hopefully will arrive in June from China if things get open. And then 2 PhD students on this topic will start in August and 1 in next March. At least from my side, it has been delayed because even though I got funding, I couldn't get enough people. But in terms of testing, I see now a few people. I mean,
a few groups.
I start to see a few works coming out. I mean, Rui is doing some great work on mutation. I talked to him, and also I think this there was a paper in ICST on this quantum fuzzing, and also there was a very good, really good paper from in I think Uppsala, which was on this on testing and debugging, supporting, because as we were talking about doing these repetitions, and they did some work on projection based to reduce the number of repetitions. So, so I think it's coming.
It's getting traction.
Yes, and especially I feel more in testing part for sure. Testing and debugging is getting a bit more attention now. So.
I had one more question, but I'm going to give other people the opportunity to do so. And again, I had a more generic question.
So maybe I think since Rui, if you have questions, you can type since you cannot unmute yourself. So.
Yes, you can type. Now, my question was more, you mentioned that one of your lead there is involved in HPC. I'm wondering what are you exploring about the connection between quantum computing and the traditionally HPC? I mean, I see quantum computing mostly solving large optimization problems, and I'm not sure that is that most of the engineering, the classical HPC engineering applications are very amenable to quantum. But again, I could be wrong. I mean, what's your take on this? How are you trying to bridge this gap, let's say?
So I think what he's trying to do is not something very, theoretical. He just wants, because we have this national experimental exascale infrastructure. It means that we have this mandate to provide the resources, computing resources to researchers and so on. So the idea we are trying to do is that we deploy different simulators, quantum computer simulators on the infrastructure, and we provide access to universities for teaching and so on. So we are not trying to build anything specific related to quantum computers. It's mostly that using existing open source quantum computer emulator like with Qiskit or so on, and then we give access to students to do their projects and so on. And
yeah,
researchers.
I can see using a quantum computer as an accelerator to some
Yes.
specific class of problems,
Yes.
and maybe restructuring some of the problems as optimization problems, and then you could basically make a big dent in some of the applications for the traditional matrix-based or sparse matrix-based kind of things, finite element methods. The paradigm is totally different, and it's so radically different at this point that I don't see an immediate gap bridging.
I mean, for us, it's just simply deploying. Because if I run on my computer, it takes too much time. So if I run on his infrastructure, it can save me a lot of time in experiments. So it's very simple thing we are doing. So
got it. Okay. All right. Well, I don't have any other questions. I don't know if either Jean-Paul or any other people who might still be online here have any questions. I don't see anything in the chat. So I would wrap it up. Thank you again, Shaukat, for your time and for your insightful presentation. Unfortunately, I could not appreciate everything of what you said, but at least I got a good gist of it, which is good. And I hope to basically have an update maybe next year or in 6 months about how you guys are doing, and hopefully you will have a larger team and even more and better results.
Yes, of course. I hope.
Okay, so. Thank you very much. And I also would like to take this opportunity to remind the remaining audience that we have another presentation in 2 weeks' time by Andrzej Miransky from the University of Toronto in Canada about also quantum computing and software engineering, how to do this interpenetration, let's say. So, okay. Thank you, Shaukat. Hope to see you one of these days in person. Thank you, everybody, for joining us, and hope to see you soon.
Thank you. Bye-bye.
Okay, bye.